Swayam Prabha. Digital India. Educated India.
In this lecture, we are going to continue with our discussions on Hamilton-Ostrogradski principle, which we had started off in our previous lecture. We are going to discuss further on Hamilton-Ostrogradski principle for dynamical paths and look at deriving the equations with external forces. So, we are going to look at the equations of motion. We start with an example of a simple pendulum with horizontal forcing as shown in this figure. The generalized coordinate is theta. Therefore, the Lagrange's equation, there is only one Lagrange's equation, and with that external force q. In this situation, right now we do not know what is q, and we are going to find that. The left hand side of this equation happens to be standard. We have discussed this before. We have the kinetic energy in this form, potential energy, gravitational potential energy with the x axis of the datum. This is Lagrangian, and we have the partial derivatives of the Lagrangian. Everything up to here is fine. We have discussed this. What is new is the right hand side of this equation written as the capital Q, which is the force that is acting, generalized force that is acting on the system. Now, how do we calculate generalized force? For this, we are going to follow the steps that we took in expressing the virtual work in terms of first the physical coordinates and then going over to the generalized coordinates. Okay, how do you express work? What is the work done by this force? The bob of the pendulum is moving in xy, in the xy plane. The force is acting in the horizontal direction, therefore, its representation is F I cap dot. This is the displacement of the bob, delta x I cap plus delta y j cap. This is the displacement of the bob, and because of this dot product, therefore, I have only f delta x. Now, can I express this x in terms of theta? I do, I can express x as a function of theta. Then let us do that. X is nothing but L sin theta. As you can see, this is the x, this is L sin theta. Therefore, it is the variation of L sin theta. And what is the variation of L sin theta? L is the constant quantity, L cos theta delta theta, and this I must read out as my capital Q. This part times this is the variation of the generalized coordinate. Therefore, whatever multiplies that to give me work, that quantity must be the generalized force. And here notice that theta is an angular coordinate. Therefore, this generalized force must be a moment, must have dimensions of moment of a force. We have identified therefore capital Q, F L cosine theta, and therefore, our equation of motion is simply whatever we have derived, and on the right hand side this is F L cosine theta. F can be a function of time in general. You can have a little more simplification, and that is the equation of pendulum with a horizontal force. We move to the next example. Here we have a pendulum on a cart and this bob of the pendulum is connected to a dashpot, a viscous dashpot, and here even though I have shown that this dashpot, one end of the dashpot is completely grounded, you can imagine that what I intend to discuss is a pendulum which is damped only for the horizontal motion. Therefore, as the pendulum swings, only the horizontal motion is damped. The damping force acts only in the horizontal direction. Now, the generalized coordinates, in this case we have x and theta. Therefore, we have two Lagrange's equation of motion. On the right hand side of the two equations, we have the generalized forces, corresponding generalized forces, which I represent as capital Q theta and capital Q x. The left hand side is completely known, we have discussed this before. This is the Lagrangian, x axis shown is the datum. Now, we have to find out the generalized force, how to find out the generalized force. Therefore, we have to start from work. To find out work, we start from the position of that bob. Position of that lowercase m, the bob, is x I cap plus L sin theta I cap minus cosine theta j cap. This we have discussed before. Velocity of the bob, etc., we have discussed in the when we derived the Lagrangian. Now, when we write down the work done by the dashpot forces, what is the work done by the dashpot forces? What is the force? What is the force that acts from the dashpot? Now, dashpot force, if I write F d, it is minus d times the velocity in the horizontal direction, in other words velocity in the x direction. What is the velocity in the x direction? That we know from the expression of velocity of the bob. Therefore, minus d times velocity of the bob in the x direction, that is the force, and that is in the I cap direction, and dot product with the variation of the position vector of the bob, that is work. This is virtual work, that is why we are taking variation of the physical coordinate of the bob. So, virtual displacement of the bob, the force dot the variation or the virtual displacement in the physical coordinates domain, in the physical coordinates of the bob. And I can write down from here the variation of the physical coordinate in terms of the generalized coordinate. Here, when I take the variation operator acting on the position vector of the bob, as you know that variation operator is just like a total derivative operator, except that it does not vary time. Therefore, this is delta x coming from here, and from here it is L delta theta cosine theta, and plus this is cos theta becomes minus sin theta, that is why it is positive, and that is in the j cap direction. This is the variation of the physical coordinate or the virtual displacement, what is also known as the virtual displacement in the physical coordinates, and this expression we will use in the virtual work. And when I do that, I get this expression, and this must be written in terms of one part in terms of delta x. This contribution is from the virtual displacement in the horizontal direction, one generalized coordinate, and this is the other generalized coordinate, the angle of the pendulum, and we have these coefficients which are then the generalized forces, corresponding generalized forces corresponding to those generalized coordinates. The first coordinate is a displacement coordinate, therefore, q x, capital Q x must be a force, so that the dimension is work. The second generalized force, capital Q theta, is getting multiplied by an angular coordinate variation. Therefore, capital Q theta must be moment, must have dimensions of moment, so that the product of q theta delta theta is work. And I can read out this capital Q x and capital Q theta and just recall what our equations of motion were. The Lagrange's equation, the left hand side structure by now it should be familiar. On the right hand side we have capital Q theta, and if you do all those standard steps, you will get on the right hand side, which is the new term, which is capital Q theta. In the same way, you can derive the equation of motion corresponding to the displacement coordinate. On the right hand side, we have here the force. This is the force, generalized force in the x coordinate direction, and here we have, this has the dimensions of moment, this has dimensions of moment. So, this is how we derive the equations of motion in the presence of external forces. We will continue this discussion with another example. This is a charged particle or a bead sliding on a hoop which is rotating. We have and this is the whole system is in a uniform vertically upwards magnetic field. This example without the magnetic field we have already discussed. Now, we will bring in the magnetic field and calculate the force on the charged bead and derive the equations of motion. Now, the generalized coordinate for this system was theta, this we had noted before, and the equation of motion is this. The new thing is on the right hand side, capital Q theta, which is a generalized force corresponding to this coordinate, and because this is an angular coordinate, you should guess that capital Q theta must be some moment. Now, Lagrangian is kinetic energy minus potential energy of the system. We write down the position vector of the bead, which we have done before. We have calculated the velocity of the bead. The hoop is rotating at a constant angular velocity, capital omega. And finally, we had calculated this before, the velocity square of the bead, and the kinetic energy is half times mass times velocity square, and the potential energy is minus mgr cosine theta, where the datum is the xy plane. Remember that this xyz coordinate system is not rotating with the hoop, it is a fixed thing. Therefore, this is the Lagrangian. These things we have discussed before. Now, what is new is the generalized force, that is what we have to calculate, the generalized force. We start again with the virtual work done, that is equal to the force dot the variation of the position vector or the virtual displacement. Now, what is the force on the bead? Is a charged bead moving in a magnetic field. You know from Lorentz force, you can calculate force on a charged particle in a magnetic field, moving in a magnetic field, as charge times velocity cross the magnetic field, E times Vm cross B, and the magnetic field is in the z direction. Therefore, its representation is some magnetic field strength times k cap. Rm, the position vector of the bead, is shown here in terms of the generalized coordinate. Vm, which we will need in the force calculation, is obtained by time derivating the position vector, which we have done before also. Now, the force which is E charge times V m cross B, I have done this cross product and I leave it to you to work out the details. I have taken a this cross product I have done, and this is the final expression. This is the final expression, straightforward calculation. Apart from that, we also need this delta R m, which is the variation operator operating on the physical coordinate, delta R m, which should be easy. It is nothing but the total derivative operator, except that it will not derivate the time. Here we have time in the expression of R m. Therefore, when I take the variation, only this sin theta variation we have here, sin theta variation, here cosine theta variation. Therefore, the virtual displacement delta R m in terms of so this is the virtual displacement in the physical coordinates, and this is written in terms of the virtual displacement in the generalized coordinate space or the configuration space. We are talking about variations or virtual displacements in the generalized coordinates, or which means in the configuration space of the system. Therefore, delta W, if you take the dot product of the force and delta R m, it turns out to be this simple expression E r square capital omega sin theta cosine theta delta theta, and this should be representable as some capital Q theta, the generalized force, times delta theta. Once again note the virtual displacement in the configuration space is an angular coordinate. Therefore, capital Q theta must have dimensions of moment of a force. Therefore, we read out what is capital Q theta, the generalized force in the coordinate direction theta. And once that is done, rest of it is straightforward steps. We have to do the partial derivatives of Lagrangian, and finally, we write down the equation. The right hand side we have the generalized force, and we just plug in that value or that expression. That completes this example. Let me summarize. We looked at examples to demonstrate the Hamilton-Ostrogradsky principle to derive equations of motion of systems with external and non-conservative forces. So, with that I will conclude this lecture.